Welcome Abaqus users, welcome to my tutorial. Today I'm going to be doing a nonlinear buckling analysis of a channel section. Why am I using channel section? Because it's something I've been doing, it's some research I've been doing in my free time. So I think this tutorial is going to be very helpful for everyone who are doing a nonlinear analysis of asymmetrical cross sections like L section, Z section, etc. Okay, so let's move to this short presentation I've made for you so that I can explain what are we going to do in a very brief time. So as I said, we are doing a nonlinear buckling analysis of a channel section. So our beam is going to be 2.8 meters long, subjected to 4-point bending. So why am I using 4-point bending? Because in between the forces you have bending without the shear stresses. So on this lower picture you can see that I have some additional elements on the web. I will explain to you why am I modeling that way. So if we look at the channel section, we can see that the center of mass and the shear center do not coincide. Because of that, if we apply force through the web or somewhere on the flanges, which is something that will probably occur in real life, then we will get torsion as well around the shear center. That's why I will be modeling the force through the shear center, and I will be adding additional shell elements so that our force would go through shear centers and we will have only bending. If you want to do eccentrically loaded channel section, it's much easier. You just put the force on the web or on the flange. So since this is nonlinear buckling analysis, we need to include the nonlinear behavior into our model. So we have three types of nonlinearities. It's material, geometrical nonlinearity, and there is also residual stresses. So first, material nonlinearity. What we usually assume in our calculation that all materials are linear elastic, but that's not true, especially with the structural steel. Its behavior is mostly plastic, and that's why I will be using today a bilinear stress strain curve of the steel. I'm using structural steel grade 355. You can also use more complicated curves like multilinear curves. They will give you more accurate solution, but for this tutorial I think this is more than enough. So then there is geometrical nonlinearity. We can see on the picture that any type of element is not perfect. During the production it kind of develops this initial bow, and that's why it will show nonlinear behavior. And then there is also issue of residual stresses. They occur because during the production of the parts of the cross section do not cool at the same rate, and that's why the residual stresses develop along the cross section. So how are we going to include nonlinearities into our model? So first, material nonlinearity we will include by using bilinear stress strain curve, as I showed before. Residual stresses are a bit more complicated to include into your model, so I'll be using, let's say, simplified method, which is quite accurate. So we will be using geometrical nonlinearity as well as residual stresses. We will include them in our model with something called equivalent geometrical imperfection. So what does it mean? We will model imperfection that is larger than the real life imperfection of the model, and that way we are going to include both geometrical nonlinearity like a initial bow and the residual stresses by using imperfection. So since I'm from Europe, I'm using Eurocode, and according to Eurocode we can see this table. For channel section, buckling curve D is assigned, and also we are using plastic analysis, so the size of our imperfection is going to be the length of the beam divided by 100. So in our case, if we have 2.8 meter beam, We divide that by 100 and we will have 28 millimeter imperfection. So 28. Results. I will also show you how you can extract data results from your Abaqus model. In this case, I will be showing you load displacement curve, how to do it in Excel. After I show you how to do load displacement curve, I think you can figure out on your own how to extract any type of data. And so just one last slide to show you what will be the process of our analysis today. So first I will make model 1, which I will be using to conduct linear buckling analysis. Then by extracting some data about linear buckling, I will include nonlinear behavior into model 2. When I say nonlinear behavior, I will include imperfections, and the stress strain curve we will include later in the model. Then we are going to do nonlinear buckling analysis. I'm sorry, here it says linear buckling, it should say nonlinear buckling analysis below the model 2, so I apologize for that. So let's move on to the new model. So here we are. I will be doing everything from the scratch because I think it's the best way for me to show you, to teach you how to do a nonlinear buckling analysis. So first we need to create part. So click here, create part. And I need to mention that I will be using solid elements, or how Abaqus called them, brick elements. ANSYS called them solid, but anyway, while I'm doing this, I'll just go back to my PowerPoint presentation. So what we have here is a hot rolled section. So in between the web and the flanges, you have this curved part called the radius. And if you use shell elements, you cannot include the curve into your model, and what that's going to do is affect the torsional stiffness of your cross section by as much as 10 and 20 or 20% even. That's something I've found out while doing my research on channel sections. If you're using shell elements, you definitely need to modify your model to make up for torsional stiffness. You can modify it by using additional beam elements, which is more complicated. That's why I'll be using solid elements in my analysis. So let's get back to Abaqus. So click solid extrusion, continue. Now I will just type in the coordinates of my cross section. You can just follow me. I think that's going to be the easiest for you. So click here, create lines connected. So go here into this window and type the coordinates. So click first coordinate 18.5 minus 70. Click enter. Oh, it's here, we can see it. Now the next coordinate is 70 minus 70. So basically what these coordinates are, they represent the edges of the cross section. Click enter again. So 70 minus 80, 0 minus 80, 0, 80, 70, 80, 70, 70, 18.5, 70. Click enter and click escape now. Now go to create lines again and type in the following coordinate 6.5, 58. Click enter. Then 6.5 minus 58. Click enter again. Now click escape. Now use this option called the create arc. Click on that and we will just do the radiuses. So click here, click on the other edge, click here, click on the other edge, and basically you are done. So click escape and go here, done. Now it's asking us the depth of the extrusion. In our case, the depth of the extrusion is equals to the length of the beam. In our case, that's 2800 millimeters. So click OK and the beam will generate now. Right now, I told you I need to do the additional shell elements, so I need to do some partitions in order to make the generating of the shell elements easier. So go to create partition, click here. I'll be partitioning the edges of our beam, so select this option, select midpoint, datum point. So I'll be clicking on this edge and on midpoint, which is somewhere here, I can barely see it. Yes, click here, create partition. Now do the same for the lower edge. So click on the edge, select the point on the edge, it's the midpoint, and yes, create partition. Now do that, we will do that 2 times, actually 4 times more. Now I'll be partitioning this edge, and I'll be clicking here on midpoint, create partition. Now this edge, I don't see midpoint, it's here, create partition. Now this edge, this point, create partition, and one last time, create partition. Okay. Now we can do the shell element. So use this option, create shell, extrude. Click here, select the plane. This is the plane we will be drawing on, and select an edge. So basically you can select this edge. It's not important. And now you can see the midpoints that we've created, and it will be much faster to do the shell element. So click here, click escape, and it's done. So the Abaqus is asking us the depth. So the depth equals to the distance between the shear center and the web of the beam. In our case, it's 22 millimeters. I will not be showing you how to calculate the distance of the shear center from the web, but you can do it in Abaqus. You can find maybe some data on the internet about geometrical characteristics of your cross section, but I think it's the most accurate way to do it is to use Abaqus to calculate the distance of your shear center from the cross section, from the web actually. So in our case, I measured it to be 22 millimeters exactly. So I'll click OK. And we need to do one more shell. So let's just repeat everything. Create shell, select plane, select edge, use this, create lines, click here, click escape, click done, and enter 22 millimeters again. Okay. So what else do we need to do? I will now create a set. So why am I doing it? Because I need that set later when I will be extracting data for the low displacement curve. So click on the sets, create set, call it set 1, select the geometry, this is the point I need, and click done. So it's set 1. And yes, one more thing I need to do is to create partitions. So I'll be partitioning the edges of the shells because I need to add force to the middle height of the shell. So I'll be just clicking the same option, edge, select midpoint, click on the edge, click on the midpoint, right, this one, create partition. Do the same thing on the other shell. Click here, create partition. Okay. So basically we are done with the part. We need to go to property now. First we need to create material. So we can call it Stell linear, and the only property we need to include in eigenvalue buckling analysis is elasticity. So Young modulus, I'll be using 210 gigapascals, and Poisson ratio is obviously 0.3. Click OK. Now we need to create two types of cross-section, one for the solid element and one for the shell element. So first we'll call the first one solid. It will be for the solid element, homogeneous, continue. The material is steel, click OK. Do the one more for the shell, I will call it shell, homogeneous, continue. It's asking us the thickness. I'll be using 10 millimeters, but basically if you have a real experiment that you're doing, then you will add the real thickness of the steel plate that you will be welding on the web of your cross section. So I'll put 10 millimeters. Material is still linear. Click OK. Now we need to assign the section. Click here, assign section. First, I will click on the solid part of our beam. Click done, and the section is solid, of course. Sorry. Okay, and click done. Now you have assigned the section. We need to do it again. Click assign section. So the regions is this shell. Hold the shift key. Click here as well. Click done and just put shell. Okay, so yeah, click done, sorry. So let's move to the assembly. We just need to create instance. We will create instance from parts, dependent. Okay. The next step is to create the step. So I will click here, create step. What we need, I will call it step 1. We need a linear perturbation and use buckle. Click continue. Everything is okay. Number of eigenvalues that you request, let's put 10. It's not actually, you only need the first one, but we will put 10. Vectors, we will be using per iteration. Well, Abaqus suggests 18. I think that's okay. And maximum number of iterations. Sometimes when you put lower number, the solution may not converge, so put 300. Okay. Now we can go straight to the load. We don't have any interaction. Click on the load. So first create load. We can call it load 1, concentrated force, continue. So spin your model. The way, I don't know if you know this, but the way you use this, how to spin the model, is by clicking Control and Alt key at the same time and then your left mouse button. So select, let's move to the loads again. Select point for the load. First this one, click done. We are doing eigenvalue analysis, so 1 Newton is what we need. Click it there. Do the same step again. Concentrate force, continue. Click here, click done. And the size of the force is still -1. Now we need to create the boundary condition. There is more ways to, let's say, model a simply supported beam. I'll show you how I do it, and I get pretty accurate results, so I think this way is correct. So first, on this edge, and on this edge as well, hold the shift key. So click done, and the only degree of freedom I'm going to restrain is in Y direction. Click OK. So let's move on. Now click boundary condition again, displacement rotation, continue, and this point right here I will use pinned boundary condition and click OK. And one more time, create boundary condition, displacement rotation. What I'm going to do now is select this point and also these 2 points. So hold the shift key, this one, and what I'm going to do is restrain displacement in x direction, and in that way I'm getting what we call a fork boundary condition. So our beam can twist around the y-axis as well around the x-axis, but torsion of the beam at the supports is restricted, and also the warping of the beam must be free. So click OK. Now boundary conditions are created. We need to go and mesh our part. So click on the mesh. First we need to seed part. Sorry, click here. Now you can click seed part. Global size of 1/4 is way too rough. Put 20. And it's okay. Now, okay, click done, sorry. Now move on to assign element type. I need to assign element type to the solid part of the model. Why? Because if you use this 8 node brick, I used to, sometimes I would get really inaccurate solutions in linear buckling analysis, so I moved to 20 node brick element, and this one gives me much better solutions, so I'll be using this one. OK, yes, click OK, and click done. Now we can just click on mesh part. So click OK, and our part has been meshed. After the meshing is complete, we can move to, we need to copy the model. So I said we will have two models, one for linear analysis, for linear buckling analysis, and one for nonlinear analysis. So let's copy the model. So this is how you do it. Right click, select copy, name it model 2, and OK. Now go to model 1 and go to job. Create job. For the model 1, call it job 1. You can call it job 1. So click continue. And before I submit the job, there is one thing we need to do. So click on the model 1 and edit keywords. I will explain to you what are we doing now. So click here, click enter, and type in the following: node file u. So what this does is creates one file with the information regarding the eigenmodes, so we can later call upon that file to include the imperfections in our model. So click OK now. And now what you need to do, go to job. What I recommend doing is first data check. In there, if everything checks OK, then you submit the job. Click OK. When the job is done, I will meet you back. So my linear buckling analysis is complete. So let's click results. So this is the first eigenmode. You can check the higher eigenmodes, first, second, third, fourth, fifth, etc. They pretty much look as the way you would expect them to look. So now what you need to do is look at your eigenvalue. So in our case, our eigenvalue is 63,782 newtons. I've used the commercial software called the LT Beam, which gives the almost exact solution. In LT Beam, I got 64,950. So that's, of course, it's not 100% accurate, but I think it's really, really good result. So we need to remember these eigenvalues. So now let's move to model 2. As I said before, we already have defined model 2, but we need to make some adjustments so that we can conduct a nonlinear buckling analysis. So first, let's move to part model 2. So first what we need to address is the material. So we have defined the linear steel, which is not okay for nonlinear analysis. So we will delete this material and we will make a new one. I will call it steel nonlinear. And now first I will include elasticity. So Young modulus is still 210 gigapascals and Poisson ratio is still 0.3. But now I will put the plasticity also. So first the yield stress is 355 megapascals and plastic strain at yielding is 0. And the ultimate strength is 510, and we said that the ultimate deformation is 20%, that means 0.2. Okay. Now we need to address the sections. So the solid section and the shell section were made from linear steel, and now we need to switch to nonlinear. So click OK, go to solid, do the same thing, and that's basically it. The next thing is the step. So we have defined a linear buckling analysis in the step 1. Now we need to make a new step. So click here, create step. Step 1 is okay, and now we are using static Rix analysis, which uses the arc length method. So click continue, include non-linear geometry and incrementation. Well, you can put 1000 increments. The length of the increment, I think the best is 0.01, and estimated arc length, well, we will leave 1, but I think that the arc length is probably going to be more than 1. But anyways, so now we need to repeat the load and the boundary condition, because whenever you delete an old step, the load and boundary condition also are removed. So first, let's define the loads. So click here, create load, load 1, concentrated force, click continue, and add load here. Click done, and put the eigenvalue 63,782, and of course it's minus. Now do the same thing again, but now put it on the other shell, click done, and again minus 63,782. Click OK. Now let's define the boundary condition. So click create boundary condition. I'll just repeat the boundary condition from the model 1. So on this edge and on the opposite edge, hold the shift key, define, actually restrain the movement in direction 2. Now let's just pin this point right here. So continue, click on the point, click done, and now again create boundary condition, click continue, and restrain the movement in x direction is in these three points. So hold the shift key and click done. Okay. So now we need to define a new job. So I'll click here, create model 2, job 2, continue. And before I submit the job, I need to edit keywords. So go to model 2, edit keyword. So what you need to type in is the following: So click here, click enter, and type in this imperfection. File equals job 1, step 1. So what this means, we are applying imperfection, file from which we are using the file we created in job 1, so it also has the name job 1, and the step is of course 1. So click enter, and now write this, which means that we are using the imperfection from the first eigenmode and we are multiplying it with 28. Click OK. Now go to job, click here, first do the data check and then submit the job. And when the job is done, I will meet you again. So my analysis is basically complete. When you're doing a RIX method, it will never be completed like the eigenvalue buckling analysis was. So I'll show you what I mean. Go to the results. And now go to load proportionality factor. So this is our load and on the y-axis, and this is the arc length. So we can see now that the load is decreasing, so the peak value is reached. At that point, you can terminate the job. So just go to job 2, kill. Is it okay? Yes, it's okay to kill the job. And it's terminated. Now let's go back to results and I'll show you what do we have. So right here you can click animate time history and you can see your element buckling. It's I think it looks really cool. Oh. And it's something you would expect how the buckling of a beam should look like. So now I'll show you how to extract the results. So first go to create XY data. Click here. Click on ODB history output, continue, and what we need is a load proportionality factor for the whole model. So click plot, this is it. Click X, so just go to edit data. In the X column you have the arc length, and in the Y column you have your LPF. So I'll show you what you need to do. Copy it, go to Notepad, and click paste. Why are we copying it to Notepad? Well, the reason is quite trivial. We just want to replace the point with comma because we're copying this to Excel. So replace all, go to escape, click copy, click here. Okay, so this is the load displacement curve of my previous models. Copy it here. So click paste. And what you need to do, well, this is 0 obviously. You need to multiply the LPF. In our case, it was, I don't remember, 63,782. Click OK. Actually, yeah, what I will do is I'll type in like this 63.782. I'll use the kilonewtons instead of newtons because that's in civil engineering kilonewtons are used more frequently. Now let's get back to this. Click cancel, go again to create XY data. So this time click ODB field output and choose the unique node. And which node do we need? We need the node set. At the beginning of the video we made the node set called the set1, and it was the node at the midspan of the beam. You can choose any node you want, but I think the displacement at the midspan is most commonly place where you measure the deflection. And in this case, we are going to check for the displacement in x direction. So let's just get back to the model. Yeah, it's x direction, so it's u1. Plot. Go again to edit and copy the displacement. Again, the displacement is in the right column, in the left column is the arc length. Click copy, go to notepad and replace the points with commas. Replace, comma, replace all. Now copy this to Excel. Click paste. And now what you can do is use this data and this one as well. And go to insert, I think, scatter, maybe this one. And then you can, of course, modify your curve. I don't know, put like displacement here, load here. This is exactly the way we would expect our load displacement curve to look like. We can see that the peak value is around 44 kilonewtons. You can use your engineering codes to calculate the ultimate load and compare it to this one. I think this is a bit higher value than I've calculated using Eurocode, but that's pretty normal because codes are usually a bit conservative. So that's basically it. I hope you liked my tutorial. If you have any questions, leave them in the comment section. If you like the video, please click the like button. You can subscribe. You don't have to if you don't want to. And if you want some other tutorial related to, I don't know, static structural problems or buckling analysis, I can do a tutorial. It's no problem. I really hope you enjoyed it and it was helpful for you, and I hope that if you're doing this kind of buckling analysis in Abaqus, that by watching my tutorial you will have much less problems than I had.